Hi folks, and welcome back to Physics with Captain Rod. I'm making this video here to describe for you how a transformer works and what it does. So before we chat about transformers, we're going to chat about this here. Okay, so the magnetic force. The magnetic force acting on a charged particle moving through a magnetic field is calculated by taking the charge times the velocity of the particle crossed with the magnetic field vector. So you really have to have kind of a basic understanding of that before, to understand some of the rest of this video here. So magnetic fields act on moving charges. We'll kind of start with that. All right. Now, over here now, this is kind of a very common basic circuit type of question or problem when studying magnetic fields. What we're looking at here is imagine this being conducting material, with this conducting bar here that's on top, free to slide, and these are magnetic field lines. Now, if I were to apply a force in such a way that the bar started moving this way with some velocity here, I'll just say V, and we looked at a positive charge carrier in the metal, if you do the V cross B part, fingers parallel to this, rotate till your palm is towards the magnetic field vectors, you would conclude that you'd have a force on that particle in this direction. So basically that means that all positive charges in this bar are going to feel a force in that direction. All the electrons here will feel a force in the opposite direction, down. The electrons, remember, are free to move. So in reality, what's going to happen is it's going to cause, let me go back and get rid of this. It's going to end up and cause electrons to move clockwise through this closed loop. Electrical current, however, is based on positive charge carriers. So the positive current that we would assign to that is actually in this direction. Now we would have both a current and a voltage. The voltage, right, that's called induced voltage. I'll draw it on the metal bar here, would have, whoops, looking for blue, would have this polarity. Now it's not that there's an actual battery there, but the movement of this bar would create a tendency, a push, if you will, for positive charge carriers to move counterclockwise, via this Q V cross B force. So basically we would describe that as saying there's a voltage with this polarity. Now, that voltage is called an induced voltage. And what I like about physics is there's different ways you can think about things. All right, it is in fact, this type of thing that's happening, but you can also describe this phenomenon via the idea of magnetic flux. So a quick little review. Magnetic flux is basically field strength times area. And, times the cosine of the angle between the magnetic field vector and the normal, but that's not important for this discussion. We have a magnetic flux through this area right here equal to this product, the field strength in the region times the area. Now, when magnetic fluxes are changing, we don't get any currents or voltages, but when magnetic fluxes are changing, we do. And I've already got videos on the math of why this is, but I'm just going to summarize it here. The voltage induced through these loops is equal to the rate of change of magnetic flux. This is known as Faraday's law of induction. Whoops. Get back to my screen here. There we go. Sorry about that. Okay. The math for it basically is this, that the induced voltage, I think I'll write it up here, is equal to the change in magnetic flux over change in time. This right here is known as Faraday's law of induction. Now, let me kind of get rid of this stuff, and we'll start talking about transformers now. All right, so in this picture, what we're looking at is we got this iron core here with a bunch of wires wrapped around it, N1 times on the left, N2 times on the right. Now we're going to imagine that we hook this to a DC voltage source and a switch. I'm going to center this. And we're going to chat about what happens when we close the switch. So with the switch closed, we would expect a current with this polarity. Whoops. I should say in this direction right here. And right, that's because of the polarity of the battery and assuming positive charge carriers. And that current is going to create a magnetic field in the interior of the iron that's this way. You can get that by just kind of mentally grabbing onto the wire right here with your thumb in the direction of the current, and remember that your fingers will roll around in the direction of the magnetic field lines. Now, basically what that's going to do is create us an electromagnet. Now I'm going to go ahead and draw field lines here. I'll do them in blue. So basically, oops, do that one a little better. Basically now we've created our electromagnet, field lines in this orientation. Now, $1,000,000 question I usually ask people, is there a magnetic flux over here? And the answer is yes, on the right-hand side. Second question, is it changing? And if this is a DC source, now the current, when we close a switch, will go from 0 to some value pretty fast. I'm not talking about that part. After that initial 0.1 seconds or 1 second or however long it takes, after that, the answer is no, it is not changing, that this flux is constant. So what do we expect for an output voltage here? And the answer is nothing, because by Faraday's law of induction, remember, induced voltages are equal to the change in magnetic flux over change in time. Now, the way I'm formulating this right now, this would be per loop. I'll talk about how the number of loops come into play here in a minute. Now, long story short, DC voltage here gives no output here. Now, I just asked my class, how could we change this to make this effective to get a voltage out, and everybody had a pretty good idea. We can change this to an AC voltage source. Because now what will happen is our current is constantly changing direction, and our magnetic fields will now be constantly changing direction. So our flux now is changing sinusoidally here on this right-hand side. Now, what does that mean? We're going to get a voltage out now, long story short. So we got a voltage in and a voltage out. And by Faraday's law of induction, the input voltage we can write as N1 times change in flux over change in time, because this is per loop. But there's N1 loops over here. And on the other side, we can say that the output voltage is N2 times the change in flux over the change in time. Now the change in flux and the change in time, that has to do with the number of blue field lines here, which is the same on both sides. And it's not too difficult of algebra to put these together and have that your output voltage is equal to N2 over N1 times your input voltage. So this device, this schematic, if you will, is the schematic for what's called a transformer. And what it does is it's used to change voltage. Right? It works with AC voltage only, and you can change voltage either higher or lower. If N2 is bigger than N1, your voltage goes up. If N1 is bigger than N2, your voltage goes down. All right. Other things that may show up when you're working transformer problems. The power on the input side, I'll put power in, is equal to current in times the voltage in. Your power out is equal to your current out times your voltage out. No, the O is good enough. Now, then the $1,000,000 question, are these two things equal? And the answer is typically no. This process will generate some heat. There's almost always some energy loss, but that doesn't mean we can't at least approximate it as so. So when you're working your homework, look for the word ideal transformer. If the transformer is ideal, then you can say, okay, then my power out is equal to my power in. Or sometimes efficiencies are given. You know, an efficiency might be 0.85 for 85%. If an efficiency is given, you can say that your power out is whatever your efficiency is times your power in. So this is meant to be just kind of a quick introductory video on transformers. Let me kind of go over this again. Schematically, this is kind of how they work. What do? They change voltage either up or down, and typically according to this equation here for doing the voltage calculations. And they only work for AC circuits. They don't work for DC voltage sources. This is probably one of the main reasons why our power grid is AC. It's not probably the only reason, but I'm sure it's probably one of the largest, because these devices are very easy for changing voltage up or down. And for anybody watching this, if you never, if you're interested and you don't even know what does a transformer look like, when you go home tonight, or if you're already at home, just walk outside and look for the power line. And what you should see, all right, it's a big pole. It looks something like this, and it'll have this big round thing here. And then the line will go, there'll be some lines that go to your house. That's the transformer. The voltage on this side heading to your house is 120 volts RMS. The voltage on the other side of the line is probably around, I'm kind of guessing here, but probably around 5,000, give or take, because electrical power is generally transmitted at high voltage to minimize I²R losses. And by the way, it's maybe 5,000 on the other side of that transformer, but if you get quite a ways, like between towns, it's much, much higher than that, probably 20 or 30,000 volts. So anyway, that's Captain Rod's description of transformers in 12 minutes or less. I hope that you enjoyed the video. Have a great day.